Hey there, ATSEVS533 students. Dr. John Shruggy is here today to tell you all about Lecture 4B, which is going to be our examination of regional climate change. Now, as you're going to see, we're not going to even really attack the whole issues of like how climate will change in some location or some other location or so on in general, because as you're going to see, that turns out not to be the most productive way to learn about such a thing. You know, pretty much everything that we have learned so far this semester has been anchored into this idea of global climate change. We worried about, like, global changes in the radiation and energy budgets back in the second module. We looked at large-scale changes in the temperature distribution and precipitation distribution and so on back in the first module and so on. Even, you know, when we talk about things like regional, we talked about, like, the difference between land and sea. We didn't get all bogged down of, well, this is what's going to happen in coastal Australia, and here's what's going to happen in the rainforests, and so on. That's just not in general, excuse me, I bumped this thing here. That's just not in general what we're getting interested in at this point, despite the fact that these regional climate changes kind of are what global climate change says. I mean, I think it was somewhere in the reading in the IPCC AR5 that, you know, it talked about the fact that you can think of global climate change as just sort of the sum of lots of regional climate changes, all of which are different, and all of which are manifesting in all kinds of local ways. I mean, these are the changes that affect the lives and the environment and so on. They decide, I made a little ticker across the bottom there, they decide important things like what we eat and what we grow and how we live and how we use water and how diseases spread and how the ecology and the economy work and how national security is affected and so on. Some of these things are pretty obvious. I mean, clearly what we can grow and what we can eat in a region are obviously very closely related to regional climate change. You might be less clear about things like diseases and so on, but clearly that could be things like spread of mosquitoes. I was involved some years back, actually, in some research projects that were about how mosquitoes spread under different climate change scenarios, and it's complicated. And the mosquitoes are merely the vector of the disease. They are, in fact, just carrying pathogens like malaria or West Nile or whatever. So you also have to worry about like how climate change affects the life cycle of the pathogen. It's all very complex. Obviously, there's ecological changes, there's changes in how the regional economy works. If you have migration crises and so on, there's national security implications. This is the stuff that matters. This is what the public really wants to know. Well, that's going to be a little unsatisfying because, like, as the IPCC Fifth Assessment Report states, regional climate change projections are generally more uncertain than projections of the global mean temperature. While overall we actually have pretty good confidence in things like how the global mean temperature will be changing between now and, say, the end of the 21st century in different scenarios and so on, what that means for individual regions gets a lot more complicated for a lot of ways. And the IPCC report really only lists two important ways, and I'm comfortable with that. Let's talk about it in that context. They're saying that there is natural climate variability that becomes very important on the regional scales, and there can be changes in land use that are very important on regional scales that become big complications in our ability to make regional forecasts of what the climate is doing in any given location. Let's focus on these land use changes first. Numerical models of the climate system, based on the 7 primitive equations and so on, are in general driven by boundary conditions that are developed by Special Report on Environmental Scenarios and so on, or the RCP pathways and so on. But they don't, in general, incorporate specific, like, regional ideas, like, we think there'll be more development of irrigation projects in this part of sub-Saharan Africa. That would be a really interesting and important thing to include in a model, but we don't really try even. Okay, there's just so much uncertainty as to where we would do it, how we would do it, etc., that things like changes in land use. We believe more of this arid land will be converted to row crops, or we believe more of this forest will be taken down due to the sprawl of suburbs. The truth of the matter is we just don't know that much about like those land use changes and so on. But those kind of land use changes will end up having very large impacts on the regional climate of the future in these locations. And actually, two important ways come to mind. The so-called Oasis Effect and the Clothesline Effect. Both of which are examples of ways in which we can make a change to the land use and end up changing the transport of heat and water vapor from the surface into the atmosphere. Okay? The source of heat for the atmosphere is the surface. The sun warms the ground, not the air. And the source of water is at the surface. Let's pick these apart real quick here. There's the Oasis Effect. The Oasis Effect is when a place that was, previously dry or surrounded by dry conditions or whatever, now becomes very moist. I mean, you can picture this like an oasis in the desert, like what I have in the background of this slide or something like that, where like now we have a source of water vapor, but it's dry in all regions here around it. Or this could be, say, an irrigation project out in the middle of some arid area of Arizona or something like that. But either way, it is a patch of ground where there is wet soil moisture, wet conditions. Well, when there is warm air transported over this now wet location, when there is heat advection over that, to use the correct jargon here from the glossary of meteorology, you can get these enormous rates of evaporation off of the surface. You can get strange heat fluxes, or conduction, if you will, between the hot air and the relatively cool ground. This is all really complicated and really important since the sources of heat and moisture are at the surface. By adding an area of moisture surrounded by dry conditions, you can really make very dramatic changes to the rates of evaporation and conduction of heat at the surface. If it's about the soil moisture, or, well, the moisture of the surface, like adding a lake or something like that, or whatever, some kind of oasis of moisture, we call it the Oasis Effect. And the Oasis Effect is a thing in meteorology. Okay, we worry about the Oasis Effect of various, reservoirs and things like that. So it can be a little hard, let's just to separate this out here. The core idea of the Oasis Effect is this idea that regional changes in land use, like putting in irrigation projects, like what you see here in this here, create changes in the soil moisture, and then that results in changes in evaporation and conduction of heat that, frankly, it's pretty much impossible for the model to predict or anticipate. I mean, the model just has no way of guessing that 20 years into the future we're going to have a big irrigation project and there's all this green stuff going on in a place that's currently arid. That's going to have a huge impact on the local climate because of the Oasis Effect, and the model, if the model knew it was there, the model could handle the Oasis Effect. That's no big deal. But the model doesn't know that those things are going to be built. That puts a whole lot of uncertainty into what the regional climate looks like. It's a little bit subtle, but I do want to bring in the equally important clothesline effect. We can make changes in how we use land, like go from bare land to irrigated cropland, or go from bare land to an orchard, or go from like a forest to bare land, or something like that. We can make changes in how we are using land that set up what is called the clothesline effect. Now, to understand the clothesline effect, you kind of have to know how a clothesline actually works. I mean, we all understand you put wet clothes out there on the line, and they dry. But there is actually kind of a subtle little buried thing here in this whole idea of the clothesline effect, and that is, notice where we put the clothes. We put them up, where they would catch the wind. You don't dry your clothes by laying them out on the ground. Okay? You dry your clothes by putting them up in the wind where they can catch more wind. That is called the clothesline effect. Specifically, it's, to use the jargon of meteorology, it's about changing the roughness of the surface. If we just let this clothes sit on there, if we just took our clean laundry and laid it on the grass, the surface is not very rough. If we put them up on clotheslines, they are a bigger obstacle to the flow. We call that roughness. There's a roughness to the surface. The flow has to go over more things. And the roughness of the surface is a very important parameter in determining the evaporation rate and the conduction rate. I almost use the words flux of moisture and flux of heat. Same thing. And so changes in the roughness can produce changes in evaporation. It would take forever for your clothes to dry just laying on the ground because the evaporation rate wouldn't be that high. put them up as an obstacle to the flow, make the surface rougher, to use jargon of meteorology, and you get a much larger evaporation rate. Well, again, things people do change the roughness of the surface. We can go from bare ground, which is relatively smooth, to row crops, which are rougher. That changes the roughness of the surface, changes rates of evaporation, changes rates at which heat conducts from the surface to the atmosphere. That's the clothesline effect. Or we could go from maybe grassland to putting in orchards. This happens in, say, sub-Saharan West Africa when they put in coffee plantations or banana plantations or something. You might be going from, say, grassland to trees. Okay? A land use change has changed the roughness of the surface, which then changes the rates of evaporation and conduction and so on. That's called the clothesline effect. Again, that's a really hard thing for the model to handle. Well, not exactly. If the model knew we were going to make a change, if the model knew, hey, this used to be this rough, but now we're changing it to a coffee plantation and it'll be this rough, the model could handle it just fine. The problem is the model doesn't have that information. The model has no way of knowing that we're going to make a change 20 years from now because of changes in the economics of coffee production, and now we can have more of these coffee trees over here, whereas we used to have low row crops or something. The model has no way of knowing. If it knew, it probably could make a good regional climate forecast, but because it doesn't know about how we're making changes to the evaporation and making changes to the conduction heat, the model can't do it right. Now, here's the deal. This idea of the Oasis effect and the clothesline effect will certainly be on the next test. And I'm not sure that I gave a great explanation, especially if some of the very basic stuff in here wasn't quite what you knew. So here's the deal. You might know that back when we had a Department of Atmospheric Sciences at Creighton, one of the things that happened there was we had a program on the radio. It aired on AM radio stations out in the country. Farmers and tractors listened to us talk about weather. Sometimes it was about the weather that was happening. Sometimes it was more of like a fundamentals of meteorology. And believe it or not, I believe it was episode 505 of our show back in 2009 was about the differences between the clothesline effect and the Oasis effect, which must have been fascinating to the people listening. But anyway, I am going to try to embed that video the audio of that program right now into this video. I don't know if it's going to work. If not, there'll be a link to the actual audio of episode 505 on Blue Line and the webpage that you're currently looking at, and you can just pause this video and go listen to them there. So depending on how it worked, you're either going to hear this right now or go get that link. It's only about 5 minutes long.
From the Creighton University Department of Atmospheric Sciences, this is Weather Break for Friday, April 17th, 2009. I'm Dr. John Schrage. Folks who aren't meteorologists are often surprised by how interested weathermen are in the surface of the Earth, and that's understandable. It seems like the soil and the plants and the surface of the oceans would in fact be the least interesting thing to people whose job it was to monitor and predict the weather. However, as we've seen several times over the years here on Weather Break, the surface of the Earth is hugely important to the atmosphere, and that's because the surface of the Earth is where most of the heat and all of the water vapor in the atmosphere come from. As we often say here on the show, it's important to remember that the sun doesn't warm the air. The sun warms the ground, and the ground warms the air. Figuring out exactly how fast the soil temperatures will increase, and in turn how fast that heat will get transferred from the ground up into the atmosphere, is a fundamental part of meteorology and the atmospheric sciences. In much the same way, all of the water vapor or humidity in the atmosphere starts off as water at the surface of the Earth. This water then either evaporates off the ground directly, or is pumped from the soil to the atmosphere by plants through their roots and leaves. But either way, the water vapor ends up in the atmosphere, and will eventually condense and form clouds and rain. Again, the rate of this transport of water vapor from the ground to the atmosphere becomes hugely important to meteorologists, since it tells us a lot about the humidity in the air. A big part of forecasting, therefore, is about getting the rates of heat and moisture transport between the surface and the atmosphere right. This is not an easy problem, because the conditions can change so quickly at the surface of the Earth, both from place to place and from time to time. For example, the rate of water evaporation off the surface will be completely different over a city, which is made mostly of pavement, than it is over a farm, which is made mostly of dirt. Even over the city, the rate of evaporation will be different over, say, a parking lot than over a golf course or a park or something like that. Figuring out exactly how these different surfaces interact with the atmosphere is extremely complicated work, requiring lots of observations and lots of theoretical work. A classic problem in meteorology involves understanding how a region of taller vegetation will affect the rates of evaporation around it. For example, picture a grove of trees surrounded by low crops like soybeans or alfalfa. Both the crops and the trees are in the business of moving water from the soil to the atmosphere via their roots and their leaves, so both types of plants are causing evaporation and adding water vapor to the atmosphere. However, the trees are much taller. They catch more wind than the lower crops do. Therefore, they have a greater evaporation rate per unit area than the crops do. The trees are better at moving water into the atmosphere than the crops are because the trees catch more wind. A clothesline works in much the same way, which is why when you want to dry your clothes outside on a line, you hang them up high. By catching more wind, the clothes on the line will have a faster evaporation rate and will be dry sooner than if, say, you just draped the wet clothes on the ground or something like that. This business of how trees or other examples of tall vegetation produce much more evaporation than the surrounding plants is actually pretty important when a meteorologist is trying to get the forecast right, and the phenomenon is now called the Clothesline Effect. Lots of parts of the world see pronounced examples of the Clothesline Effect, where evaporation rates and humidities are unexpectedly high because there are patches of trees or other tall plants surrounded by broad areas of shorter plants. Forecasting the humidity and ultimately the clouds and the rainfall over these regions can be a challenge because of the Clothesline Effect. Actually, there's a related phenomenon called the Oasis Effect. When you hear the word oasis, you're probably thinking of something like a beautiful garden with ponds and pools out in the middle of a desert, and that certainly would be an example of an oasis. However, from a meteorological point of view, the Oasis Effect can happen anytime there's an isolated moist region surrounded by drier conditions. For example, a lake surrounded by relatively dry grasslands will produce an oasis effect, and sometimes so will a region of irrigated crops that's surrounded by dryland farming conditions. The idea of the oasis effect is that the amount of evaporation that will happen over the oasis will be much more than the meteorologist would normally expect, since the air that blows in from the surrounding regions will be very dry. As any farmer who irrigates his crops can tell you, when a dry wind blows across irrigated fields, the soil dries out much more quickly than you would probably think possible, and that's the oasis effect in action. We'll have links to more information about the Clothesline Effect and the Oasis Effect, and frankly, humidity in general, on our website. That's weatherbreak.creighton.edu. This has been Weather Break, which is produced by the students and the faculty of the Department of Atmospheric Sciences at Creighton University for KINI-FM, St. Francis, South Dakota, and KBRB in Ainsworth, Nebraska. Have a good weekend, everyone.
Alright, so hopefully you listened to that audio there, that episode of Weather Break, as much as anything else, established the context here of this business of the Oasis Effect and the Clothesline Effect, so that you understood how they were important to the climate system, as well as the difference between them. Okay, by all means, let me know if you have any questions about the whole business of the Oasis Effect and the Clothesline Effect. No matter what, though, I mean, there's also going to be other reasons why we are uncertain about regional impacts of climate change. That's, remember, what we're worried about right now. We're worried about this idea that we are generally less certain about what's going to happen regionally than what's happening globally. And there is also just a fundamental modeling challenge here. Remember, we are trying through the IPCC report to understand climate change in the context of the Fifth Assessment Report and an ensemble of 42 climate models that are each members of this big ensemble. Well, the problem is there's just a whole lot of regional variation among the different members of the ensembles. Of the 42 climate models, there is generally good agreement on the global trend. By and large, we actually have fairly narrow error bars or uncertainty on like what we think the global mean temperature will be like under certain scenarios. by the year 2050 or by the end of the 21st century. That in and of itself is not such a huge problem. But in terms of individual locations, it turns out the models are not all that often in consensus. There will often be a lot of variability from one model to another as to whether they think there'll be more warming or more cooling. Will the climate be wetter or drier in this individual location? And there's actually a lot of reasons about that, mostly about internal variability. Remember, last lecture we talked all about the internal variability of the climate system, stuff like El Nino and monsoons and quasi-biennial oscillation and so on. Plenty of regions of the world, their climate and the climate variability is dominated by those kind of processes. Here, let's take Peru over here in the corner of South America. Peru's climate is heavily dominated by its connections to what's going on in El Nino and La Nina. So your ability, let's not make it so personal, your climate model's ability to make good forecasts of what the regional climate of Peru is going to be like pretty much depends on your climate model's ability to understand what's going on with El Nino and La Nina, and how El Nino and La Nina might be changing associated with forced climate variability like global warming or changes in anthropogenic aerosols or something like that. So if you can't model the internal variability very well, and or you can't model how the internal variability might end up changing due to the forced climate variability, you have no real chance of understanding what's going on with the climate of Peru. Okay? You can certainly still get a good handle of what's going on globally, but that regional impact becomes a big problem. And the truth is, lots of places on Earth, a significant chunk of the total area of the Earth is dominated by these internal sources of variability. I mean, almost a third of the area of the Earth is affected by monsoons, if nothing else. So, this is a real problem in modeling, and it's easy to just throw up your hands and say, I guess we just don't know. And I don't know is a good answer, okay? But we do have to find some way eventually to move forward with this before the 6th assessment report, which I don't know when that's due. See, here's the deal. Even though these regional climate changes are hard to get a hold of and depend on sensitive things that we don't even really feed to the model as input, like irrigation projects and macroeconomic changes in the agriculture businesses and stuff like that. And yeah, all these regional climate changes are definitely going to be real. Okay? There are places that are going to be warmer. There are places that are going to warm more than other places. There are going to be places that are drier. There are going to be places that dry more than other places. There are places that are going to be wetter. There are going to be places that their increase in precipitation is more than others. We really need to start getting a handle of these kind of processes. And to be honest, our best bet to understand them, at least in the short term, is to start looking at the observations. To forget about models for the time being, or at least use the past as a way to start understanding how to interpret the models. So, for example, here is a plot of temperature anomalies across the United States. This happens to be 1991 to 2012, so it's like a 20-year, 21-year period or something like that, compared to a period back in the mid-century. And unsurprisingly, it's almost all warmer, right? We would expect that overall the climate has gotten warmer, and you can see it's not, huge, because I'm only talking a period of, a few decades. But on the other hand, somewhere along a degree or so, degree and a half of warming, Fahrenheit, a degree and a half of Fahrenheit of warming across most of the United States seems pretty typical until you actually take a look at what, it's the southeast United States, maybe even specifically like Alabama and Mississippi and Arkansas and so on, where there really isn't that much warming, and in fact, maybe it's even a tiny bit of cooling since the middle of the 20th century. What the heck's going on there? And that looks like the kind of thing we want to know. That looks like we are having some kind of regional climate change. The climate of, the lower Mississippi Valley or southeast United States or something like that is clearly doing something different than the larger scale. That sounds like what policymakers need to know, economic planners need to know, the public needs to know. This is an example of the kind of phenomenon that's important right now and very much key in climate science. Now I'm going to use the word global warming holes to describe this. Where there's this idea that there's a hole in the global warming. Not because like somehow there's less carbon dioxide or methane or something here. Let me go back to the term global warming hole first. That's a tricky word, okay? Some climate scientists really hate the use of that word. Others use it in their scientific publications, okay? The idea, though, that I liked, rather than get all bogged down in why there's reasons why that's a problematic word and so on, I like the idea of using it in the context of this course because, I mean, it kind of gives you a picture of what we're looking for here. We're looking for things like places where global warming is not apparently happening due to some kind of regional climate processes. So even though the word, I mean, like if you go forth at a job interview and use the word global warming hole, you might be using the H word. You know what I'm saying? Some climate scientists are not happy with that word. But the idea here that there is some kind of regional process going on in the southeast United States, especially in the lower Mississippi Valley, that is somehow or other keeping global warming from affecting that area is very real. And just to use a quote from the page, this is from NOAA, the NOAA website, you can get the link down here. Researchers have also connected the cooling trend in the southeast United States to periods of thick clouds and unusually high soil moisture. Thick clouds decrease the amount of sunlight reaching the surface of the earth, and the damp soil allows for high evaporation rates, preventing daytime temperatures from getting as warm as they otherwise might. In other words, there's a big Oasis Effect going on over the southeast United States. Oh, so, you know, global warming and probably the Gulf of Mexico is getting warmer. There's more evaporation when when warm, moist air masses, maritime tropical air masses from the Gulf of Mexico move up onto the southeast United States. They're producing more precipitation. The soil is staying moister. And as a consequence, we get an Oasis Effect going where we're keeping the surface cooler. We're producing more clouds. Oh, well, that's pretty cool, actually. And the southeast United States is not the only known global warming hole. And it's not clear that that will continue as weather patterns shift. Maybe maritime tropical air masses from the Gulf of Mexico arrive in the southeast United States less often, and this will produce changes in the regional climate, as is the case any place where there's these kind of global warming holes going on. But this idea that this might be the kind of thing we need to be looking for is kind of fashionable right now in climate science. People are writing software that goes through the terabytes of data that come out of these climate models looking for regional changes like this. Can we find regional areas where, oh, look, for a period of a few decades we had a global warming hole where something like a local Oasis effect was actually causing temperatures to not rise, at least for a few decades, in those regions. Very important as to how climate science is looking for. Now, again, if you looked forward in the IPCC report, you can see a big chunk of chapter 14 was all about expected climate changes in the Arctic, expected climate changes in South America, expected climate changes in Australasia. Okay. Most of those are pretty uncertain. There's very little consensus between the 42 models, and frankly, it's all pretty regional. I mean, I'm not sure that many people are all that excited, at least people in this class are all that excited about, you know, climate change in southeastern Africa being, you know, confidence in it is low. Well, I don't think that's so important. I mean, no, it's important for the people who live there, but I mean, in terms of the pedagogy of the course, I don't think that's important. I wanted you instead to understand why our uncertainty is so high, why our certainty is so low, might be a better way to put that, about these regional climate changes and like the surface processes like the Oasis Effect and the Clothesline Effect that drive them. Alright, before we go and be done with this lecture, I just wanted this to, after 4A was such a long lecture, I wanted one that was a little bit shorter for you. Let's answer, though, 3 or 4 quick questions about what you just learned. Climate scientists generally have blank confidence in their predictions about future changes in the global climate than they do in their predictions about climate for a particular region. Is that less confidence or more confidence in their global forecast than in their regional ones? Make a choice from those 2 options and get a little feedback before you move on to question 2.